I'm very happy to be here to have this opportunity, especially because this conference to honor Jose Antonio, my old friends and respectable friends for, I don't know, more than 20 years. So today's talk, I start some historic event between Spain and Sendai. Sendai is a place I used to work. Okay, the historical event starts with mission from Sendai to Spain and the Vatican. The first mission from Japan set sail from Sendai. And Sendai is more like Galicia. The coastline, you have a lot of areas, and the sea is rich with fish and oysters, shellfish. So we have the same kind of good fish and maricos. So that is and 500 years later, Jose Antonio came to Sendai with a kind of mission and to have collaboration and exchange of information and so on. So after that, I'll talk to DSP. I'm afraid the screen is too small to see from the behind. So first, DSPs and sugar tera and biotoxins. I'd like to explain briefly of our effort to produce reference toxins. So, as I mentioned, first Japanese mission set sail from Sendai. He's Tsunenaga Hasekura, and this ship was built in Sendai, supervised by Spanish military. So it's a very like Spanish ship. It started from Sendai and went to Mexico and near the Sevilla, Madrid, Vatican, and came back via Madrid, Sevilla, Mexico, Philippines, and Sendai. So it's about 500 years ago, the missions started from Sendai. So we are going to have 500 years anniversary for the mission. Unfortunately, this ship, replica, was in Sendai, washed away by tsunami. So now it's started to rebuild this ship for demonstration to memorize our exchange between Spain and Sendai. And another thing connecting Sendai and Galicia is unfortunately this kind of organism. As I said, we have very similar environment, oceanographic environment, and we have Dinophysoidea and this kind of DSP toxins. So when DSP outbreaks is known, I'd like to show that younger Jose Antonio. In 1988, immediately he came to Sendai to share the information and to promote collaboration. And that's very lucky for me. Because of his visit, we had opportunity to visit Galicia, and that opened the gate for Japanese group, myself, to have a relationship with scientists in Galicia and beyond Galicia. So we are very grateful to him. And it's too small to read, but this is an agreement between University of Vigo and Tohoku University. We had the agreement, exchange of scientific results, and also we hope to have academic program exchange. We are planning to materialize this agreement to put the program set by Jose Antonio on track. And I'm hoping to send somebody to Galicia and inviting somebody to Sendai. We are trying to do this and to honor Jose Antonio starting this project. We like to materialize this program. Okay, now let me allow to move to the topics. Ciguatera is a fish poisoning, not common in this area, but quite common in Pacific, Caribbean, Indian Oceans. And today I'm talking mostly on the Ciguatera in the Pacific. And I'm sorry, you can't see the detail, but in the Pacific, we find two types of ciguatoxin. The basic skeleton, we can divide 1B type or 3C type. When I say 1, 2, 3, it's order of addition from the column. 1B is more polar and comes earlier to the other one. 4B is the last to come from the column. And A and B means stereochemistry at this position. Anyway, the dinoflagellate Gambidiscus produce this precursor toxin. And fish oxidize the two terminal parts of the molecule attaching hydroxyl groups. So when the toxin goes up food chain, you have polar oxidized toxin. And using small amount, we could determine 23 analogs. But most difficult part is to prepare standards for analysis. Anyway, you are successful to prepare most of the toxins and obtain this chromatogram. And thanks to the advanced technology nowadays, we can detect very low level of toxins, all kinds. We apply this analysis to fish we obtained in Okinawa, southern part of Japan, where Ciguatera outbreaks is known. And we see the toxin profile are different from fish to fish. And this difference is not individual variation. This profile is specific to fish. We tested fish from different areas of Okinawa and collected in different years, and we all find same toxin profile to the same species. I'd like to comment on this later on. And to our surprise, we find only ciguatoxin 1B type toxin in fish from Okinawa. And against our previous notion, sugar toxin 1B is not always major toxin. Sometimes we have other toxin as major component. And we have tested maximum 30 specimens, and we found variation is quite small because toxin profile is shaped by enzyme of the fish. And that means when we test fish, by just testing 2-3 fish, we can predict the toxin profile of the fish. And toxin profile is important when you apply enzyme immunoassay. So it's not necessary to test many fish to know the toxin profile. And here is fish toxicity against body weight. And in this way, body weight increase. And I can comment 2 things. One is big fish not always most toxic. Even smaller than this one can be toxic. So you can't tell the people you can eat this fish because it is small. No, it is not correct. And also, you see the highest toxicity we get from this fish is 1.8 microgram per kilogram. Very small amounts. So, you know how much effort you have to put to obtain pure toxin from fish. And because the gummy discs produce unoxidized precursor toxins, we have to purify this toxin from fish. And when we tested toxin profile, fish from Okinawa area contain mostly sugar toxin 1B type. So that means gummy discs inhabiting this area produce only 1B type toxins. On the other hand, fish from the north of Okinawa produce only 3C types. So gummy discs in the north and south produce different type of toxin. And there is a biological line, boundary, what is named Watase line, that separates biota, fauna between north and south. And it seems gummy discs north of the line, south of the line, produce different toxin. But when we test the fish from Marcus Island, that is to the middle of Hawaii, contain both CTX1B types, 3C types. So there must be gummy discs producing 2 types. And when we tested amberjack from Hawaii, we observed 2 types of toxin. One of the reasons it is possible that because amberjack is a migratory fish, they feed different places to accumulate different types of toxin. But when we tested gummy discs collected in French Polynesia, it produced 2 types, 4A, 4B, and 3C. That means this strain could produce 2 types of toxin. And you can see that there's no sugar toxin 1B or oxidized form of sugar toxin. So in the Pacific Ocean, we say Okinawa, we know the toxin profiles in Okinawa. And in the Marcus Island, in Hawaii, we know the toxin profile. And the fish in Indian Ocean is known to have different type of toxin, but we don't know if fish migrating this area can have two types, or fish this side of ocean has Indian Ocean type or both Pacific Ocean type. We have to test to know. And depending on the toxin profile, we know we can apply ELISA test or not. So, as I said, toxin profile is shaped by enzyme of fish. And that enzyme is genetically fixed to fish. And I wanted to know what happens in human body and what kind of enzyme is oxidizing. So we tested enzyme from human origin and also microsome from human origin, and mixed sugar toxin 4A4B with enzyme or microsomes and incubated and analyzed. This is a very preliminary experiment, but I like to mention the concentration of the toxin or substrates in the reaction mixture is very low. So we cannot expect high recovery of the products, but we could see by this CYP3A type enzyme. CYP means a cytochrome P45 type toxin, which oxidizes foreign material and inactivate and make it soluble into water for excretion through urine. So with this enzyme, we detect CTX1B, and with microsome, we detect 54-deoxy type toxin at a very low concentration. But anyway, we certainly obtain these oxidized products by using enzyme. So the human is doing the same thing with fish. Fish do this, and we do this in the same way. And also, by using this enzyme, maybe we can oxidize this kind of toxin, which we can produce in quantity by culturing dinoflagellate to obtain this oxidized toxin. That is much easier than extracting from fish. So, okay, I don't have much time, so I proceed. And now I proceed to elucidation of biotoxin by LCQ-TOF-MS. Biotoxin analogs are widely distributed among marine life. And so we need rapid and sensitive methods to distinguish toxins by structure. Okay, this structural information is necessary for monitoring and to tell, the source of the toxin we found in animals. So method is positive and negative LC-MS-MS. And the result, negative by applying negative ion MSMS, we get a good information about the cleavage site of CC bond. On the other hand, positive ion provides information about the position of hydroxyl group in the molecule. We are the first to obtain oscillation B biotoxin analog from diamond flagellate. We named this oscillation D, and I'm sorry, you can't see that detail, but the difference between biotoxin, oscillation is here. These groups are different between the two compounds. And in some cases, we have difficulty to determine the presence or absence of hydroxyl here by NMR because signals are very congested. But by using LCMS-MS, we can easily detect presence or absence of hydroxyl at this position. And when we compare biotoxin oscillation D by mice toxicity, the difference not very big. But for example, oscillation B doesn't have hydroxyl at 45 position. So presence of one hydroxyl group at 45 position makes big difference in toxicity. So we need to know what kind of structural information, all kind of structural information to convert LCMS data to toxicity. And LCMS can do this kind, can provide this kind of information. And we collected oscilloscopes from Okinawa. And what I'd like to say is we tested 23 clones, strains from Okinawa, and only 3 of them produce toxins. So don't be too much excited when you find oscilloscopes. Not all of them are toxic. Okay. Again, too small to see. Well, screen is too small, or compound is too big to see in the detail. So today, I'd like to talk about 3 toxins we obtained from Okinawa. Because our strains obtained from Ike Island, we named this IK2 strain. And I like to propose always we need to put the strain number or code to identify the source of the compound. By morphology, you cannot distinguish in detail. And by molecular formula, you can distinguish different toxins. So to indicate the source, we always put IK2, and by negative and positive spectra, they produce M-H, M plus H at almost a comparable intensity. And by negative ion spectra, its baseline background noise is small. You can clearly see the site of CC bond cleavage. On the other hand, positive ion spectra shows many ions produced by dehydration from the molecule. And this negative ion spectrum we have reported more than 15 years ago and shown all the major cleavage site, so we can easily identify the segment. And as I said, most important toxin fragment we obtain by cleavage of this vicinal dual structure. In the case of biotoxin, biotoxin doesn't have hydroxyl here, so no significant cleavage of this. So this peak is very useful to distinguish biotoxin type or biotoxin type or oscillation type. And as I said, this fragment is useful to detect hydroxyl at this position, and so on. So then I move to the positive ion. Looks more complicated, but actually it is not complicated. And by MS, we see many ions, but MS are simpler than this one. And we find many of them are produced by dehydration. Again, here. And we can follow this dehydration by checking the accurate mass, like this. And sometimes this always 18 mass unit corresponding to 1 molecule of water. And in between, we see another series of dehydration. Again, the same way, and we can accurately determine this is caused by dehydration. So we can draw the structure based on the accurate mass. For example, you start from here, and after this hydroxy is lost to form double bond, and next, again, another loss of hydroxy here, and then so we can obtain this conjugated polyene structure that contains information about the position of hydroxyls. This conjugate polyene is possible only when we have hydroxy at right position, either on alpha carbon or beta carbon to the double bond. So we can read many polyene structure from the spectrum. The same way, when we test biotoxin A, IK2, we can assign this fragment by negative ion spectra, and by following this conjugated polyene in positive ion spectra, we can tell the position of hydroxyls. Still okay? And all the same procedure with biotoxin A2. We follow dehydration and confirm this difference corresponds exactly water loss. And we can draw a series of conjugated polyene structure that reflects the position of hydroxyls. And now I talk about biotoxin D and E, that we cannot get good separation on LC. So we decided to analyze the two of them as a mixture. And by molecular formula, elemental composition, we know D and E has one extra oxygen. So we need to know the position of this extra oxygen atom. And by checking negative ion spectra, we can easily find the partial structure from here to here is the same. So difference must be from here to here. And by checking negative ion spectra, we can deduce extra oxygen here. Because it is a mixture, another oxygen D has here. So we have to assign position of oxygen atom in this fragment. This is a mixture, so spectra may look complicated, but if you see it closely, we can know they contain two sets of spectra. One from biotoxin D, another one from biotoxin E. The ion peak from biotoxin E is stronger than ions from biotoxin D. And we observe biotoxin D and biotoxin A have same partial structure. We find with agreement between fragment A and D. On the other hand, fragment from biotoxin E is 16 mass unit larger than D. That means one oxygen larger than. And we can assign, because the difference of 18 mass, these two are pair, and these two are in a pair, and these two are in a pair. So by following this pair, we can also get conjugated polyene structure like this. So by comparing negative ion spectra, we find this part is the same between D and E. But D has one oxygen here. And on the other hand, we can analyze this part and assign the extra oxygen atom position at this position. So by this way, we could deduce structure of biotoxin D and E by using very small amount of sample and other mixture. I think maybe we could analyze mixture of two, but if you look carefully, maybe mixture of three can be analyzed. So we have 10 minutes. Well, we have a few minutes for questions. Okay. Just a few minutes. Now we have, Japan is now moving from mass bioassay to LCMS or instrumental assay. For that, we need to expand supply of our reference material. So the government decided to produce this by culturing dinoflagellate and applying chemistry. So for PSP, we produce toxin C1, C2 from, blue-green, and another toxin from dinoflagellate. And for obtaining pectinotoxin, we culture acuminata and feeding this microplankton. And this is a culture we do. And for PSP, we obtain C1, C2 from cyanobacteria and GTX1 from dinoflagellate. And by chemical reaction, we can produce all PSP toxins by reaction. We have optimized condition for chemical reaction. And the recovery is very good. And so we produce oxalic acid, pectinotoxin, by culturing Dinophis fortii and Dinophis acuminata, about 100 milligrams per year. And this we can produce big amounts, so to supply all the needs in Japan. Thank you very much. I'd like to finish my talk, but I'd like to thank Jose Antonio for providing opportunity to work together with excellent scientists in Galicia and other parts of Europe. And as a token of gratitude to Jose Antonio, I'd like to present a small one from Sendai. Yes. Okay,